On the 6th of August 1945, a single explosion above the city of Hiroshima changed the course of human history. In just a few seconds, an entire city was shattered by a flash of light, hotter than the surface of the sun, and a shock wave that flattened buildings for kilometers. What shocked physicists was not only the destruction, but the source of the energy. The bomb known as Little Boy did not contain thousands of tons of explosive. It contained only about 60 kilograms of uranium, a piece of metal small enough to fit inside a large container, released energy equal to roughly 15,000 tons of TNT. How could such a small amount of matter produce a blast powerful enough to destroy a city? According to the way physicist Richard Feynman explained nuclear physics, the answer lies deep inside the atom. Hidden in the tiny nucleus of matter is an enormous store of energy, waiting to be released when the nucleus is broken apart. The first mistake people make when thinking about the Hiroshima bomb is that they imagine it working like an extremely powerful version of an ordinary explosive. In everyday life, explosions come from chemical reactions. Gunpowder burns rapidly and releases gas. TNT detonates and expands violently. Fuel ignites and pushes air outward with tremendous force. These processes can be destructive and dramatic, but they all share one important limitation. They rely on chemistry. Chemistry deals only with the outer structure of atoms, specifically the electrons that orbit around the nucleus. When a chemical explosive detonates, the atoms themselves are not destroyed. They simply rearrange into new molecules while releasing a small amount of energy stored in the bonds between those atoms. To understand the scale of this energy, imagine breaking apart a chemical bond between two atoms. The energy released is tiny. On the scale of a single reaction, it is almost insignificant. Explosives like TNT appear powerful only because trillions upon trillions of these reactions happen almost simultaneously. Each reaction releases a small packet of energy, and the combined effect produces the shock wave we call an explosion. Even so, the total energy that chemistry can release is fundamentally limited. The bonds between atoms are relatively weak compared with the forces that hold the nucleus together. This means that no matter how cleverly a chemist designs an explosive, the energy will always come from the same source. The rearrangement of electrons around atoms. Richard Feynman often emphasized this difference when explaining nuclear physics. Chemical energy belongs to the outer layers of the atom. Nuclear energy belongs to the center. The nucleus of an atom is extraordinarily small compared with the entire atom itself. If the atom were the size of a large stadium, the nucleus would be about the size of a marble at the center. Yet almost all of the atom's mass and almost all of its hidden energy are packed inside that tiny region. The nucleus is held together by one of the strongest forces known in nature. This force is called the strong nuclear force. It binds protons and neutrons together so tightly that under normal circumstances, the nucleus remains stable for billions of years. But this stability hides an enormous amount of energy. Inside the nucleus, the particles are bound together with forces vastly stronger than the chemical bonds between atoms. If the nucleus can somehow be split apart or rearranged, the energy released is not just slightly larger than chemical energy, it is millions of times greater. This is where the fundamental misunderstanding begins. When people hear the word bomb, they imagine a bigger and bigger version of familiar explosives. They picture more fuel, more fire, more pressure. But the atomic bomb is not simply a larger chemical reaction. It is an entirely different category of energy release. Instead of rearranging molecules, it breaks apart the core of the atom itself. To see the difference, consider a comparison. 1 kilogram of TNT releases roughly 4 million joules of energy when it detonates. That is enough to shatter buildings nearby. But when a small amount of nuclear material undergoes a nuclear reaction, the energy released from the nucleus is so large that it can equal the energy of thousands of tons of TNT. The reason lies in the relationship between mass and energy discovered by Albert Einstein. His famous equation E equals mc squared reveals that mass itself is a form of stored energy. Under normal conditions, that energy remains locked inside matter and cannot easily be accessed. Chemical reactions barely touch it because they involve only electrons. Nuclear reactions reach deeper. They affect the nucleus itself and allow a small fraction of mass to transform directly into energy. This transformation is what made the atomic bomb fundamentally different from every weapon that came before it. When the uranium inside the Hiroshima bomb reacted, the process did not simply rearrange atoms into new compounds. Instead, some of the mass of the atomic nuclei disappeared and was converted into pure energy, according to Einstein's equation. Even though the amount of mass lost was extremely small, the multiplication by the square of the speed of light produced an enormous amount of energy. Feynman liked to describe this realization as one of the most astonishing discoveries in physics. The universe hides immense power inside the smallest pieces of matter. For centuries, humans used chemical energy from fire and fuel without realizing that far greater energy was locked inside the atomic nucleus. Once scientists understood nuclear physics, they realized that breaking the nucleus could release forces far beyond anything chemistry could achieve. The Hiroshima bomb was the first time this principle was used on a large scale. Understanding this difference between chemical explosives and nuclear energy is the first step toward explaining why the bomb that destroyed Hiroshima was so powerful. The real source of its energy was not the burning of material or the expansion of gases. The source was the nucleus of the atom itself, where nature stores energy millions of times more concentrated than any chemical reaction. To understand the true source of the atomic bomb's power, we have to move deeper into the structure of matter itself. Every object around you, every rock, every building, every drop of water, and every human body is made of atoms. At first glance, atoms seem almost empty. A typical atom has electrons moving around a central nucleus, and most of the volume of the atom is simply space. But the tiny nucleus at the center is where almost all the mass of the atom is concentrated. And more importantly, it is where enormous energy is stored. The nucleus is made of two kinds of particles, proton and neutron. Protons carry positive electric charge, while neutrons carry no charge at all. These particles are packed together extremely tightly inside a space so small that it is difficult to imagine. The diameter of a nucleus is roughly 100,000 times smaller than the size of the entire atom. Yet, despite its tiny size, the nucleus contains nearly all of the atom's mass. This extreme density means the forces acting inside the nucleus must be incredibly strong to hold everything together. One of the most powerful forces in nature operates inside the nucleus. Physicists call it the strong nuclear force. This force is responsible for binding protons and neutrons together, despite the fact that protons naturally repel each other because of their electric charge. If only the electric force existed, the positively charged protons would push each other apart and the nucleus would immediately fly apart. The reason this does not happen is that the strong nuclear force pulls the particles together with enormous strength when they are extremely close to one another. Richard Feynman often explained that the nucleus behaves almost like a tightly compressed spring of energy. The particles inside it are locked together in a configuration that stores a huge amount of potential energy. As long as the nucleus remains stable, that energy stays hidden and inaccessible. But if the structure of the nucleus changes or breaks apart, some of that stored energy can suddenly be released. This is where the famous relationship discovered by Albert Einstein becomes important. Einstein showed that mass and energy are deeply connected through the equation E equals mc squared. According to this equation, even a tiny amount of mass corresponds to a tremendous amount of energy because the speed of light squared is an enormous number. In everyday chemical reactions, the mass of atoms barely changes, so the energy released is relatively small. Nuclear reactions are different because they involve the nucleus itself, and can convert a small fraction of mass directly into energy. Inside many heavy atomic nuclei, the balance of forces is delicate. The strong nuclear force tries to hold the nucleus together, while the electric repulsion between protons tries to push it apart. In lighter elements, the strong force easily keeps everything stable. But as the nucleus becomes larger and heavier, the repulsive forces between protons grow stronger, and the nucleus becomes less stable. Some very heavy nuclei exist in a kind of fragile balance where a small disturbance can cause the nucleus to break apart. When a heavy nucleus splits into smaller pieces, the total mass of the resulting fragments is slightly less than the mass of the original nucleus. The missing mass has not vanished without reason. It has been converted into energy according to Einstein's equation. This energy appears in the form of heat, radiation, and the kinetic energy of the fragments flying apart at enormous speeds. Feynman liked to emphasize that the astonishing power of nuclear reactions comes from the density of energy stored inside the nucleus. Compared with chemical energy, nuclear energy is millions of times more concentrated. A tiny amount of nuclear fuel can release as much energy as enormous quantities of chemical explosives. That is why the uranium in the Hiroshima bomb did not need to weigh thousands of tons to produce a devastating explosion. The energy was already locked inside the nuclei of the uranium atoms, waiting for the right conditions to release it. Another important detail is that when a nucleus breaks apart, it often releases additional particles called neutrons. These neutrons carry no electric charge, which allows them to move through matter relatively easily. When they collide with other nuclei, they can cause those nuclei to split as well. This process can trigger a chain reaction in which one nuclear event leads to many more events in rapid succession. The secret hidden inside the nucleus is therefore not just the amount of energy stored there, but also the possibility that a single nuclear reaction can start a cascade of reactions. Under the right conditions, this cascade can grow extremely fast, releasing an enormous burst of energy in a fraction of a second. The atomic bomb was designed to exploit exactly this property of nuclear matter. Understanding the structure of the nucleus reveals why nuclear energy is fundamentally different from chemical energy. The atom is not merely a tiny particle, but a container holding immense energy concentrated in its core. When scientists learned how to unlock that energy, they discovered that even a small quantity of nuclear material could produce an explosion powerful enough to change the course of history. Now that we understand that enormous energy is stored inside the atomic nucleus, the next question becomes more specific. Not every atom can release that energy in a way that produces a nuclear explosion. Most atomic nuclei are extremely stable. Even if they are struck by particles, they simply absorb the disturbance and remain intact. To create a powerful nuclear reaction, scientists needed a type of nucleus that was naturally unstable enough to break apart when disturbed. One of the most important of these nuclei is uranium-235. Uranium is a heavy element found naturally in the Earth. Its atoms contain 92 protons inside the nucleus, along with a number of neutrons. But not all uranium atoms are identical. Some contain slightly different numbers of neutrons, and these variations are called isotopes. The most common isotope in natural uranium is uranium-238. A much rarer form is uranium-235. The difference between them is small, but the consequences are enormous. Uranium-235 has 3 fewer neutrons than uranium-238, and this small difference makes its nucleus much more likely to split apart under the right conditions. Richard Feynman explained that the nucleus of uranium-235 is in a delicate balance. The strong nuclear force tries to hold the protons and neutrons together, while the electric repulsion between the many protons tries to push them apart. Because the nucleus is so large, the repulsive forces are already very strong. The system is stable, but only barely. It behaves almost like a droplet of liquid that can be stretched and deformed if it is disturbed. Imagine the nucleus as a tiny vibrating drop made of nuclear matter. If a neutron enters the nucleus, it can disturb this balance. The neutron is absorbed by the nucleus and adds energy to the system. This additional energy can cause the nucleus to stretch and oscillate. If the deformation becomes large enough, the nucleus may split into two smaller nuclei. This process is called nuclear fission. When uranium-235 undergoes fission, the nucleus breaks into two fragments that fly apart at extremely high speed. These fragments are themselves atomic nuclei of lighter elements, such as barium or krypton. At the same time, a large amount of energy is released. This energy appears as heat and radiation, as well as the kinetic energy of the fragments moving away from each other. But something else extremely important also happens during this process. When the nucleus splits, it usually releases 2 or 3 additional neutrons. These extra neutrons are the key to the extraordinary power of nuclear reaction. Because neutrons carry no electric charge, they can move through matter without being strongly repelled by atomic nuclei. When one of these neutrons collides with another uranium-235 nucleus, it can trigger another fission event. That second fission releases more neutrons, which can strike other nuclei and continue the process. Feynman often described this situation in simple terms. One nucleus splits and releases several neutrons. Each of those neutrons can split another nucleus. Each new split produces even more neutrons. The number of reactions does not grow slowly. It multiplies rapidly. 1 becomes 2. 2 become 4. 4 become 8. In a very short time, the number of reactions becomes enormous. This multiplying process is called a chain reaction. The crucial point is that uranium-235 makes this possible because it releases more neutrons than it consumes during fission. Each reaction therefore creates the conditions for additional reactions. If enough uranium-235 atoms are present and arranged in the right way, the chain reaction can accelerate dramatically. However, there is another important detail. If the uranium is spread out too much, the neutrons produced by fission will simply escape into the surrounding space before hitting another nucleus. In that case, the chain reaction dies out quickly. For the reaction to sustain itself, the uranium must be concentrated so that most of the neutrons remain inside the material long enough to strike other nuclei. This delicate balance between neutron production and neutron loss is what determines whether a nuclear reaction grows or stops. In nuclear reactors, scientists carefully control this process so that the reaction proceeds slowly and produces steady heat. In an atomic bomb, the situation is completely different. The goal is to create conditions where the chain reaction grows as fast as possible. Uranium-235 was chosen for the Hiroshima bomb precisely because its nucleus is relatively easy to split and because each fission event releases several neutrons. These two properties allow a chain reaction to build extremely quickly. When enough uranium-235 atoms are brought together under the right conditions, the reactions multiply at an astonishing rate. In a fraction of a second, an immense amount of nuclear energy is released. This fragile, heavy nucleus therefore holds the key to the destructive power of the Hiroshima bomb. A single neutron striking a single uranium-235 atom can start a process that multiplies again and again until billions of nuclei split almost simultaneously. And once that runaway chain reaction begins, the release of energy becomes unstoppable. Once scientists understood that uranium-235 nuclei could split and release additional neutrons, the next realization was even more dramatic. A single fission event does not remain isolated. It can trigger other fission events. When this process continues repeatedly, it becomes what physicists call a chain reaction. This idea is the central mechanism behind the enormous power of the atomic bomb. To understand how this works, imagine the very first moment when one uranium-235 nucleus splits. The nucleus breaks into two fragments and releases energy, along with 2 or 3 fast-moving neutrons. These neutrons shoot outward in random directions at extremely high speed. If one of them collides with another uranium-235 nucleus, it can cause that nucleus to split as well. When that second nucleus splits, it releases its own energy and produces more neutrons. Each of those neutrons can strike additional nuclei and continue the process. Richard Feynman explained that this multiplication happens incredibly quickly. One nucleus splits and releases several neutrons. Those neutrons may split 2 or 3 more nuclei. Each of those produces more neutrons again. The number of reactions does not grow in a simple linear way. It grows exponentially. One reaction becomes several. Several become dozens. Dozens become thousands. In only a few generations, the number of fission events becomes enormous. The remarkable thing is the speed at which this multiplication occurs. The neutrons released during fission travel at millions of meters per second. Because of this speed, the time between one generation of reactions and the next is extremely short. In a dense piece of uranium, the chain reaction can double the number of fission events again and again in tiny fractions of a microsecond. Within a millionth of a second, the number of splitting nuclei can increase from a single event to billions upon billions of events. Every time a nucleus splits, a small amount of mass is converted into energy according to Einstein's equation, E equals mc squared. Each individual reaction releases only a tiny amount of energy, but when trillions of nuclei split almost simultaneously, the total energy becomes immense. This energy appears in several forms. The fragments of the split nucleus fly apart with tremendous speed, carrying kinetic energy. Intense gamma radiation is produced. The surrounding material heats rapidly to extremely high temperatures. All of these effects occur nearly at once. As the temperature rises, the material begins to expand violently. The expanding gases and plasma push outward, creating a powerful shock wave. This shock wave moves faster than the speed of sound and carries enormous pressure. It is this shock wave that causes much of the physical destruction during a nuclear explosion. Buildings collapse, walls shatter, and debris is thrown outward with tremendous force. But the explosion is not driven only by pressure. The temperature produced by the nuclear reaction is astonishingly high. In the center of the reaction, the temperature can reach millions of degrees. Matter in that region turns instantly into a glowing plasma. The intense heat generates a brilliant flash of light in a rapidly expanding fireball. This fireball grows quickly as it transfers heat to the surrounding air, causing the air itself to expand and rise. Feynman often pointed out that the chain reaction is essentially a race between two processes. On one hand, the reactions are multiplying rapidly and releasing energy. On the other hand, the material is expanding as it heats up. When the uranium expands, the atoms move farther apart, which allows neutrons to escape more easily. If too many neutrons escape, the chain reaction slows down and eventually stops. In an atomic bomb, the design ensures that the chain reaction grows extremely fast before the expansion can stop it. This means the energy is released in a very short time. Instead of being spread over seconds or minutes, the entire burst of nuclear energy occurs in a tiny fraction of a second. The result is a sudden and violent release of heat, radiation, and pressure, far greater than anything produced by chemical explosives. The chain reaction, therefore, transforms a small quantity of nuclear material into an enormous burst of energy almost instantly. The multiplication of fission events combined with the tremendous energy stored in each nucleus creates the devastating power associated with nuclear weapons. In the Hiroshima bomb, this runaway chain reaction was allowed to grow freely for just a brief moment. Yet that brief moment was enough to unleash a force capable of destroying an entire city. For a nuclear chain reaction to grow into a powerful explosion, another crucial condition must be satisfied. The uranium must reach what physicists call a critical mass. This concept was one of the central discoveries that made nuclear weapons possible. Without critical mass, the chain reaction cannot sustain itself and the reaction quickly fades away. With critical mass, the reaction multiplies rapidly and becomes uncontrollable. To understand this idea, imagine a small piece of uranium-235 sitting by itself. Inside this material, an occasional nucleus may split and release neutrons. but most of those neutrons will simply escape from the surface of the material and disappear into the surrounding space. Because they escape, they never strike another nucleus. The chain reaction, therefore, stops almost immediately. Even though the uranium is capable of fission, the reaction cannot grow. Richard Feynman often explained that neutrons behave almost like tiny bullets moving through the material. If the piece of uranium is too small, these bullets fly out before they hit another target. The reaction, therefore, dies out because too many neutrons are lost. For the reaction to continue, the material must be large enough so that most of the neutrons remain inside long enough to collide with other uranium nuclei. This is where the idea of critical mass appears. Critical mass is the minimum amount of fissile material required so that each fission event, on average, causes at least one more fission event. If each reaction produces one new reaction, the chain reaction can sustain itself. If each reaction produces more than one new reaction, the chain reaction grows exponentially. But if each reaction produces less than one new reaction, the process quickly stops. The size and shape of the uranium strongly influence this balance. A compact sphere is especially effective because it minimizes the surface area through which neutrons can escape. In a spherical mass, more neutrons remain trapped inside the material and therefore have a higher chance of striking another nucleus. Engineers working on the atomic bomb realized that shaping the uranium into a dense compact form was essential for achieving critical mass. Another important factor is the density of the material. When uranium atoms are packed closely together, neutrons travel shorter distances before encountering another nucleus. This increases the probability that a neutron will trigger another fission event before escaping. Increasing the density of the uranium, therefore, makes the chain reaction much more efficient. But reaching critical mass alone is not enough to create a nuclear explosion. The material must reach this condition extremely quickly. If the uranium slowly approaches critical mass, the chain reaction may begin prematurely while the material is still assembling. In that situation, the early reactions heat the material and cause it to expand before the chain reaction has fully developed. The expansion allows neutrons to escape and the reaction fizzles out in what scientists call a fissile explosion. To avoid this problem, the designers of the Hiroshima bomb developed a method to assemble the uranium extremely rapidly. Separate pieces of uranium-235 were kept apart so that each piece by itself was safely below critical mass. At the moment of detonation, one piece was fired into another piece using a mechanism similar to a gun barrel. When the two pieces slammed together, they instantly formed a single mass large enough to exceed the critical threshold. In that instant, the system passed a point of no return. The combined uranium mass trapped enough neutrons to sustain the chain reaction. Each fission event produced several neutrons, and those neutrons triggered even more reactions. Because the assembly happened so quickly, the chain reaction was able to grow for several generations before the material began to expand. Feynman described this moment as the point where the physics becomes unstoppable. Once the material reaches supercritical conditions, the number of reactions multiplies explosively. The energy released heats the uranium to extraordinary temperatures, and the material rapidly turns into an expanding plasma. But by the time expansion begins, billions upon billions of nuclei have already split. This brief instant, when the uranium crosses the critical threshold, is therefore the turning point of the entire process. Before that moment, the uranium is simply a heavy metal. After that moment, the chain reaction accelerates uncontrollably and the stored nuclear energy is released in a fraction of a second. The concept of critical mass explains why the Hiroshima bomb required careful engineering and precise timing. The explosion did not occur merely because uranium exists. It occurred because the uranium was suddenly assembled into a configuration where the chain reaction could grow faster than anything could stop it. At that point, the release of nuclear energy became inevitable, and the explosion followed almost immediately. Once the uranium in the Hiroshima bomb reached supercritical conditions, the chain reaction unfolded with extraordinary speed. In a tiny fraction of a second, billions upon billions of uranium nuclei split apart, Each of those reactions released energy in the form of fast-moving nuclear fragments, radiation, and intense heat. The combined effect produced an enormous burst of energy concentrated into an incredibly small region of space. But the destructive power of the Hiroshima explosion did not come only from the nuclear reaction itself. It also came from how and where the bomb was detonated. The bomb used in the attack was called Little Boy. Instead of exploding on the ground, it detonated high above the city at an altitude of roughly 600 meters. This decision was deliberate because an air burst greatly increases the area of destruction. If a bomb explodes at ground level, much of the energy is absorbed by the ground itself. A large portion of the energy is wasted digging a crater and throwing soil into the air. By detonating above the city, the explosion allowed the shockwave and thermal radiation to spread outward in all directions with maximum efficiency. At the moment of detonation, the nuclear reaction created an intense flash of light and heat. The temperature in the center of the explosion reached several million degrees. Matter in that region instantly turned into a glowing plasma hotter than the surface of the sun. The surrounding air was heated so rapidly that it expanded violently. This expanding fireball pushed outward against the atmosphere, generating an enormous shock wave. The shock wave traveled outward faster than the speed of sound, carrying immense pressure. As it moved through the city, it crushed buildings, collapsed walls, and shattered windows across a vast area. The pressure wave did not simply push objects aside. It slammed into structures with such force that many buildings were instantly destroyed. Wooden houses, common in Hiroshima, were particularly vulnerable and were flattened almost immediately. At the same time, the explosion produced a massive burst of thermal radiation. The fireball emitted an intense flash of heat and light that spread outward at the speed of light. Surfaces exposed directly to this radiation were heated to extremely high temperatures in a matter of seconds. Roof tiles melted. Metal objects became hot enough to burn skin. Many fires ignited simultaneously across the city as wooden structures and flammable materials caught fire from the intense heat. These fires quickly combined into a massive firestorm. As the heated air rose rapidly, it pulled cooler air inward from surrounding areas, creating powerful winds that fed the flames. Entire neighborhoods were consumed by fires. The flames spread through the damaged city. The combination of blast damage and widespread fires greatly amplified the overall destruction. Another destructive effect came from the intense burst of radiation produced during the nuclear reaction. Gamma rays and high-energy neutrons were emitted during the explosion. While the blast and heat caused immediate physical damage, the radiation introduced additional dangers that were less visible but equally serious. Radiation exposure affected people and materials across the city and contributed to long-term health effects after the explosion. Richard Feynman often emphasized that the incredible power of the Hiroshima bomb came from the concentration of energy released in an extremely short time. The nuclear reactions occurred within microseconds, yet the energy released was comparable to the explosive power of many thousands of tons of conventional explosives. Because all of this energy was released almost instantly, the surrounding air had no time to absorb it gradually. Instead, the energy produced a violent and sudden expansion that generated the devastating shock wave and fireball. Another factor that increased the destructive effect was the layout of the city itself. Hiroshima was relatively flat and densely built, with many wooden structures. The lack of large natural barriers allowed the shock wave to travel across the city with little obstruction. Fires spread rapidly through the closely packed buildings, creating a continuous zone of burning across large areas. The result was a catastrophic combination of physical forces. The initial nuclear reaction produced the energy. The air burst maximized the spread of that energy. The shock wave flattened structures while thermal radiation ignited fires throughout the city. Within moments, Hiroshima experienced a level of destruction unlike anything the world had seen before. This devastation was therefore not caused by a single effect, but by the interaction of several powerful processes occurring almost simultaneously. Nuclear energy released inside the bomb produced extreme heat and radiation. That energy generated a massive shock wave and fireball in the atmosphere. The firestorm that followed turned widespread damage into total destruction across much of the city. One of the most surprising facts about the Hiroshima bomb is something that many people never realized. The enormous explosion that destroyed much of the city did not come from all of the uranium inside the bomb. In fact, only a very small fraction of the nuclear fuel actually underwent fission. Most of the uranium inside the weapon never reacted at all. Yet the energy released was still powerful enough to devastate an entire city. To understand why this is so astonishing, we need to look again at the relationship between mass and energy. Albert Einstein showed that mass itself is a form of energy through the equation E equals mc squared. This equation reveals that even a tiny amount of mass can correspond to an enormous amount of energy, because the speed of light squared is an extremely large number. When nuclear reactions occur, a small fraction of the mass of the nucleus is converted directly into energy. In the Hiroshima bomb, the uranium fuel contained roughly 60 kilograms of uranium-235. But during the explosion, only a small portion of those nuclei actually split before the bomb blew itself apart. Estimates suggest that only about 1% or slightly more of the uranium underwent fission. The rest of the material was scattered outward before it had time to react. This happened because the explosion expanded the material so rapidly that the conditions required for the chain reaction disappeared. Richard Feynman often explained that the chain reaction inside a bomb is extremely brief. The reactions multiply rapidly, but the expanding explosion quickly tears the material apart. As the uranium expands, the nuclei move farther away from one another, and neutrons begin to escape rather than causing new fission events. When too many neutrons escape, the chain reaction stops. The bomb essentially destroys itself before all of the fuel can react. Even though only a small fraction of the uranium actually split, the amount of energy released was still enormous. The mass that was converted into energy during the explosion was only a few grams. Yet according to Einstein's equation, even a few grams of mass corresponds to an immense quantity of energy. That small conversion was enough to release energy equivalent to roughly 15,000 tons of TNT. This fact reveals something profound about the structure of matter. The energy stored inside atomic nuclei is vastly greater than the energy involved in chemical reactions. A chemical explosive requires thousands of tons of material to produce the same energy that a nuclear reaction can release from only a few grams of mass. The Hiroshima explosion demonstrated this dramatic difference for the first time in human history. Another important lesson from this event is that nuclear reactions are extraordinarily efficient at concentrating energy into a very small space and a very short time. The reactions inside the bomb occurred in less than a millionth of a second. During that instant, a tiny amount of mass vanished and became energy in the form of heat, radiation, and the motion of nuclear fragments. Because this energy was released so suddenly, it produced the massive fireball and shock wave that caused the destruction. Feynman often emphasized that the deeper message of nuclear physics is not only about weapons, but about the nature of the universe itself. Matter is not simply a passive substance. Hidden inside every atom is an enormous reservoir of energy. Most of the time, that energy remains locked safely within the nucleus. But under the right conditions, it can be released in ways that transform the surrounding world. The atomic bomb revealed this hidden power in the most dramatic way imaginable. A device small enough to fit inside an aircraft released energy comparable to the explosive power of an entire fleet of conventional bombs. And yet the explosion came from only a tiny fraction of the mass contained within the weapon. This realization forces us to rethink what matter really is. What appears to be solid and stable around us is actually a form of condensed energy held together by the forces of nature. The Hiroshima explosion was not simply a large explosion. It was a demonstration of one of the deepest principles of physics. Mass and energy are different forms of the same thing, and even a small amount of matter can contain extraordinary power. When scientists first understood this connection, it changed physics forever. The same principle that made nuclear weapons possible also explains how stars shine and how the universe releases energy on cosmic scales. In that sense, the Hiroshima bomb revealed both the destructive potential and the fundamental beauty of the physical laws that govern matter.